So my other class, for whatever reason, their video did not record. So you found your stuff? Okay, good. So we're gonna this one appears to be recording. I don't know why the last one didn't. It stinks though. All right, so how did you feel about your first lesson from the book? Like first lesson that's with physics. We're on physics now. You don't like physics? You like math. Why wouldn't you like physics?
I like physics.
Okay.
I'm not good at it.
Good.
Notes for sure.
Great.
Well,
Notes for sure.
Physical science.
Well, physical science just kind of encompasses all the other stuff like chemistry and earth science too.
I like chemistry more than physics.
Oh, good. Cool. All right, so
I like what if you like physics.
let's have a look at our notes. I'm going to share my screen. All right, so our notes are, everybody get your notes out? You got them?
Yeah.
All right. So you guys were talking about measuring speed, which you did outside today. Ta-da, ta-da. All right, so as for this frame of reference, you may also hear the term reference point or point of reference, right? So again, odd because it's the same publisher, but the younger group's book calls it a reference point. But that's what you're discussing. So can somebody explain to me why a frame of reference or reference point or point of reference is important when you're trying to discuss motion?
Describe motion accurately and completely.
Oh, there you go, yeah. Can somebody put it in their own words? Why do you have to have a frame of reference?
I don't know. I just didn't know.
So what's a frame? What is a reference point in when you're considering speed? Give an example of a reference point. Okay, here's this one. Are you moving right now?
No.
Oh, yes.
You are. You're moving in relation to what?
The Earth spinning.
To the sun. You're moving in relation to the sun. So what's your reference point? The sun. Excellent. All right, if you're sitting in a car and you are watching traffic go by and you're at a light, okay, you're stopped and traffic's going by, what is your point of reference for the motion of the cars you're seeing? Yeah, it's anything you're looking at that's not moving, right? So whatever is in your field of vision that's not moving, you have to know what's not moving so that you can describe what is moving. If two things are moving at the same time, you can't really explain the motion of those things accurately. You have to have something that's not moving. It's like your control, right? All right, so to describe motion accurately and completely, you need a what? What goes in your notes? Frame of reference or reference point, okay. And a frame of reference is a system of objects that are what? Not moving with respect to one another. Okay, excellent. So if I'm looking around the room right now and I see pencils moving and I see mouths moving and I'm comparing that to all the things around it that are not moving.
My mouth's not moving.
You were the one whose mouth was moving because you're eating cheese. I see you. All right. So relative motion. Okay.
That's early.
Relative motion is in relation to a frame of reference. All right. So basically all motion is relative, right? All motion is relative, and when we talk about motion here, like if I were to, tighten up my kombucha here and roll it down my binder.
That's gonna.
Okay, yeah, it is. That's why I'm going to give it a minute there. But when I talk about the motion of this, I'm talking about it in reference to or relative to the binder which was not moving. Now our planet's always moving, the solar system's moving, but we are trying not to think about that. We're trying to think about this. So this is going to be our reference point. So how fast are you spinning right now?
Big fast.
How much is big fast?
Like 67,000 miles.
No, nope. How much spinning? How fast are you spinning?
110.
1,100. Yeah, 1,100 miles per hour. You are spinning. Now, technically, I could have put this in kilometers per hour, but I don't think you would have understood it as well. So you're spinning at 1,100 miles per hour. How fast are you revolving around? How fast are you revolving around the sun? 67,000 miles per hour. So you're moving in one direction, 67,000 miles per hour right now, and in a different direction, 1,100 miles per hour right now, but you can't see it, right? Not unless you go out and stare at the sun or mark the sun's placement or the moon's placement. The moon's moving too, right? And you can describe the motion of the moon by using yourself and Earth as the reference point.
I wonder what would happen if everything just stopped randomly.
That would be weird.
That would be really bad because we would lose a lot of gravity actually, and that would be bad. So,
No.
what frame of reference should I use? Your frame of reference has to be what?
That one.
No, look at your notes. Your frame of reference has to be
Not moving.
meaningful in order to describe motion in a clear and relevant manner. Does it matter if when I rolled my kombucha down the binder, I described the fact that the honey bear is sitting there? That doesn't matter,
Yeah,
right?
matters.
It doesn't matter at all because it's not meaningful to the objects we're discussing.
Well, the honey bear could be like using telekinesis to influence.
But it's not.
That honey bear is not Matilda nor 11, so nothing living here.
Sky was more scared.
Okay, so distance is the length. Distance is the length of a path between 2 points. What is the shortest distance between 2 points?
The crow
SI.
flies.
The shortest distance between 2 points.
A straight line.
Straight line. Thank you, Erin. Straight line. Anybody ever help their parents out when you get in the car by entering the address you're headed to into whatever navigation system they're using? Anybody do that? So if you do, for example, like Apple Maps or Waze or Google Maps or any of those, and you enter in, like say we want to go to Brewster's, all right? If I put in Brewster's from here, it's going to tell me that the closest Brewster's is across the river, because it is. There's a Brewster's like right over there. And if I were a bird and I could fly as the crow flies in a straight line, that would be the closest Brewster's. But once I tell it to route me, and I have to go all over the map to get to a Brewster's, it may not be the closest Brewster's.
Oh yeah, whenever you ask Siri like how far away is this place, it says as the crow flies.
As the crow flies. So what's that mean, as the crow flies?
The direct path.
Wait, I asked Aaron. Yeah, a straight path. Yeah, a straight line. Because the crow flies over top of everything, right?
Yeah.
So we don't move that way very often unless you're like in a smaller space or a big clear field. Or
Abide by private property law.
yeah, we don't want to get, and it's Georgia. You don't want to step on somebody's property. You know what'll happen to you. That's exactly what'll happen to you. So the best, use the SI units best suited for your measurements. So if you're measuring, Henry, don't talk out of turn. If you're measuring from here to Brewster's, are you going to use centimeters? No. What are you going to use?
Millimeters.
We're doing metric. So what would you use? Kilometers, right. All right. And if I were measuring the width of the living room, what would I probably use?
Astronomical units.
No, we got to be an SI. So what would we probably use? Meters, right. Okay. So use what makes sense, right? Don't make life difficult on yourself and do centimeters where you don't need to do them, or millimeters where you don't. Now, if you were measuring, okay, say you're an orthodontist and you're measuring the gap in someone's overbite or overjet, what would you use? Millimeters, right? Okay, perfect. No, not micrometers. So, all right, measuring displacement. Somebody tell me what displacement is versus distance. Can someone describe that? Look at your notes. It's right there.
Displacement or distance. Distance is the length of the path. Displacement is the direction from.
So what's the difference? Okay, so let's look at the graphic. Does everybody see the graphic on your page? It's the map of the little town. All right, it says little Bobby lost Fido. Oh no. All right. So
Fido circling around the bench.
he lost Fido. Well, if you look, little Bobby's up there in your top. Little Bobby, and he's crying. Oh my gracious. He's up in the top left-hand corner. Do we see him? Does everybody see him?
Wow,
Okay.
you're really crying, man.
He's really crying, man. He's upset.
Oh yeah, brownie point.
So where was,
To do anything.
no?
Brownie point.
Where'd you find Brownie Point?
If a lost dog turns up 5 miles from his house, his displacement is 5 miles. But that doesn't describe the distance he actually traveled while wandering Avo.
Yeah, everybody caught that one already.
Friday.
Yeah.
Yeah, it's very
Watch your forums. Get the app. If you don't have the app, get the app. It alerts you sometime everybody talks. Okay.
Yeah, for
And it's already fixed on mine.
You guys use Wix?
Wix.
I don't have Wix.
Get the Wix app, and it'll ding you every time somebody says something.
use the website. But I haven't
You can use the
used
website. You can use that website, but the app's really good because it does alert you every time somebody talks. All right, so let's look at this graphic. All right, now, which line is represented by distance and which one is represented by displacement? Which one is distance and which one is displacement?
Straight line is displacement, but the squiggly boy is.
Yeah, the dash line there. Okay, So where's Fido? He's in the opposite corner, right? He's
He's out of the house.
he's sniffing the ground, and he's down there in the bottom right-hand corner.
He doesn't care about Bobby at all.
No, he doesn't miss Bobby like Bobby misses him. Bobby is
Bobby.
wailing, and Fido is like wherever. So if you say a dog turned up 5 miles from home,
What's the
so
favorite
that's
thing
the,
I'm doing?
shh. The dog turned up 5 miles from home. Then that shows you that it's his what? Distance or his displacement? It's his displacement. He's 5 miles from where he started. But look at his distance. His distance is everywhere he traveled. And if you look, he went round trees and he went across a bridge and around a bench. You see all that? So all that's the distance in the middle of the park to the left.
Oh, yeah.
So he did all of that, and that's his distance traveled, but that's not his displacement. Have you ever done the sort of thing where you were going to a friend's house and the friend lives pretty close to you, but on the way you ran to Target and then you did this and then you did that and you ended up taking 2 hours to go. It normally takes you 20 minutes, and you probably have quite the distance compared to your displacement because it wasn't that far away. You ever had that kind of experience or? Oh, well, okay. That's something. We should work on that. All right. So how do you measure displacement? So displacements is an example of what? A what? Look at your notes.
Just the direction from the starting point.
D, measuring displacements. A displacement is an example of
A vector.
a vector. Yeah. What's a vector?
A character.
Yeah. It's a quantity that has magnitude and direction, right? And direction.
But he says magnitude. I don't know if he says direction.
He says direction and magnitude in that order.
Cartoon guy.
That's the guy from Despicable Me. He's the villain named Vector. And that's what he
Vector
says is that he commits crimes with direction and magnitude. Oh, yeah. So that's him. And that's what he said. Oh, yeah. Yeah, right. You see in that picture, he's like rubbing somebody's laptop on his rear end or something.
That's his laptop.
Is it his laptop? I
That's the
don't
part
know.
where Drew's trying to break into the base, so he just like hit on the button, stuck to hit the trap,
Yeah.
so he just takes the keyboard and just rubs.
Yeah.
Like what Ben does when he doesn't want anyone touching his stuff, he just licks it.
So if you, so
Ew.
vector addition, the magnitude can be the size, length, or amount. So vector addition is adding displacements together. Okay, and that's what it's called when you add displacements together. So here's an example. Do y'all see where it says number 3, displacements along a straight line? And we have peg, all right? Y'all, I made this graphic all by myself, so there you go. Woo!
You made vector by yourself?
No, I put peg in this little town. So anyway, it says,
Had left their butcher
yeah,
shop.
wait a minute, Henry, wait. There are 11 people here. Well, 10, Michael's not here. Peg left her butcher and traveled 700 feet west down Merchant Street to the flower shop. She brought some flowers for her friend Marge. Peg took the flowers 200 feet west down Merchant Street to Marge's antique shop. Peg's displacement is 900 feet to the west, and her distance is also 900 feet to the west, because it says under letter A, just above it, when two displacements represented by two vectors have the same direction, you add their magnitudes. That makes sense, right? She walked 700 feet, and then she walked 200 feet, and she traveled a whole 900 feet. If you look at the bottom, though, it says, Peg left her butcher shop and traveled 700 feet west down Merchant Street to the flower shop. She brought some flowers for her friend Ruth. Peg took the flowers 400 feet east down Merchant Street to Ruth's candy shop. Peg's displacement is 300 feet, but her distance is 1,100 feet because she traveled 700 plus 400, but she went 700 one way and 400 the other way. So distance and displacement are not always the same. Does everybody understand that? And it doesn't have to be like opposite directions. It can be turning a left or a right, going back, going forward, anything like that, right? So displacement along a line that is not straight, that's number 4. So you can often use graphing, and then we have what we call the resultant vector, and that's the sum of 2 or more vectors. So here we go with this picture. You have a helicopter which moves as a crow flies, right? And then what's going on in the picture? What's going on in the graphic there?
Criminal, I think it's criminal.
Yep. And who's chasing the criminal?
Police car.
The
and
police-
police
okay.
car.
So you got a car thief, right? It says a car thief, and the police are chasing the car thief. So if we had measurements for each of the segments of this diagram, we could determine the distance that the police car travels. But its displacement is going to be different. What is the police car's displacement going to be exactly the same as?
The helicopter.
The helicopter. Does everybody see that?
Yeah.
Okay, so as the police car makes its way, it's going to have to travel a longer distance, but its displacement's the same.
Why did police car take that weird detour?
I don't know. Maybe the street was closed.
Yeah, he should just come.
Maybe it's one way right there. I don't know. Well, maybe
Maybe you
he's chasing the car.
Map
it's your
right.
fault.
All right, so let's look at section 2, speed and velocity. All right, now here's where we get into the math part. Oh, so fun. So speed and velocity. Speed is the ratio of distance an object moves to the amount of time the object moves.
Yeah, I feel like this is a bit
So
more like
it's-
compact. I don't like it.
Shh, Henry, wait, please. So how is it notated? It's notated as what over what? Somebody know it?
Wait, what? Oh,
Distance
speed
over
equals
time.
d
Distance over
t.
time. Thank you, Ethan. Distance over time.
Nope.
So meters per second, kilometers per hour. What do we use around here on highways?
Miles per hour.
Miles per hour, right. So again, your average speed, and you'll know this because you just did it, is computed for the entire duration of the trip, right? So your average speed is the total distance over the total time. And V is average speed, right? And then what do you call the rate at which an object is traveling at a particular moment?
Instantaneous speed.
Instantaneous speed. Now this is tricky because you think probably the way I do that an instant is like, super fast, faster than you can probably time. But truthfully, you have to time some motion, so some time has to pass. So when it says at a particular moment, moment's kind of a loosey-goosey word, right? Like if you're going to track somebody's speed over 1 second, that can be their instantaneous time. But if you're going to track how fast they move over 2 seconds, that could be their instantaneous time. Kind of depends on what's moving. If you were tracking the speed of an ant, okay, you probably would not want to use 2 seconds. But if you were tracking the speed of a race car, 2 seconds might not be unreasonable, right? Okay, so graphing motion. All right, who has done algebra?
Not me.
Who's done algebra 1?
Well, I
Okay.
haven't done it yet.
But you're doing
I'm
it?
right.
So you probably are really good at coordinate planes, right?
Oh Lord, not this again.
Sorry.
Coordinate play, I play Minecraft. I use coordinate.
All right,
Coordinate.
so here we go. I'm gonna try and make this easy. If you have your axis like, look, right? Okay.
3D or 2D? 40.
It doesn't
So here's something you can remember. Which one is the X and which one is the Y as far as which line?
X is horizontal, vertical is Y.
Very good. All right. Here's an easy way to help you remember. If you were just to continue that straight up, you could make a Y out of it, right? So the stick goes right into it. That's how you know which one's the Y. The X then obviously is the other one. So where do we put distance or position, and where do we put time?
I'm guessing
Time would go
On the
on
bottom.
X.
On the bottom.
X. Yeah.
Time's going to be down here.
Well, time could be on the Y, but it looks really dumb.
No, this is the standard way this is done.
was up.
And this would be like distance or position. Okay. So y'all probably want, in a minute, you're going to want a spare piece of paper to write, but right now you're probably okay. Okay, so, but be aware that if there's something you're not completely clear on, you're going to want to take notes. All right, so you get this, right? I've got some over here.
Thank you.
Yep. And in case you guys need them.
We don't have any paper. Make sure to click that like button for Danny VLES Star.
Why is it
I'm sorry,
not
what?
pronounce her name? Here we go.
Pronounce the middle
Thank you.
Well, he attempted. Okay, so here we go. Got that, right?
Okay.
So let's say we're gonna mark seconds. 1, 2, 3, 4 seconds. All right.
Only 4.
And let's say we're gonna mark meters. So
In total or per second?
1, 2, 3. Let's just do 4 and 4. Okay?
4, 4. It's 4, 5, 4.
All right.
16.
Okay. Y'all see that? If you look at the graphs I gave you in your notes, it says Chester Cheetah is chilling under a tree. What does that look like?
Oh gosh.
Looks just like this. Like he's not going anywhere. He's not traveling any distance over any time. It could be down here.
Chester Cheetah has got that Cheetos person.
Yes. So,
So straight line would just be doing nothing.
yes, he's doing nothing, right? He's not moving. Okay. Now, if you see a line that looks like this, here's what you need to notice about it. This will make it make sense. I hope. All right. So this is the. Let's put this here. Here.
Exponential.
Then look here. Okay. Here's your time, and here's your distance. During which 2 meters is he traveling the fastest?
3 and 4.
3 and 4, correct. Because look at how much, see how much position he covers in this small space of time? And then right here, he's covering a little less, and here is a little less, and even less. Okay, and the steeper we make this slope, the faster he's doing what would we call this kind of motion? Not just moving, but say
Exponential.
almost. What?
I was gonna say, but if he keeps that,
Wait a minute, I asked a question. Do you have an answer to the question? Okay. So we got to imagine that this graph keeps going. Okay.
If it does, when he's going to reach Mach 1 sooner.
Yeah. Okay. So what I'm asking is
Velocity.
not velocity. So this is what we would call this.
Excellent.
Okay. He's accelerating, right? Acceleration is movement in general, but in general colloquial terms, we would say, oh, he's accelerating. Truthfully, he's getting faster. That's probably a better description, actually, to say he's increasing his speed. Because we'll get to acceleration soon, and you'll find that acceleration probably doesn't mean what you think it means. But, so he is increasing his speed, right? And you can see that. It's very obvious when you look at this space right here. He covered a lot of distance. He covers 1, 2, well, 3. He covers about 3 meters in 1 second, or we should have said that these were second, and these are meters. Okay? All right. So it says he spies an antelope, gets up, and starts to chase. So that would be what this is. All right? He was chilling. Now he's like, oh, dinner, I'm gonna move. All right, gonna move fast. So let's say he's chasing now, and now you have a line that looks like this. So is he getting faster, going slower, staying the same?
Staying the same.
He's definitely going faster, because if you look, in 1 second he covered 1 meter, and then by 2 seconds he's covered 2, 3 he's covered 3. So
How's
he's
he
getting
faster?
faster,
Meters per second.
but he's okay, getting faster is not correct. He's moving forward. Sorry, that's the term I meant. He's moving forward, but what kind of rate? Before he was moving forward at increasing speed. Here he's moving forward at constant. That's what I was trying to say. Sorry, got distracted. So this is a constant rate, and it's forward motion. He's moving forward. Okay? So this says, the sentence that went with that said, Chester is running steadily towards his dinner. He's running. All right.
Did he get dinner?
Very hungry cheetah. All right, so the next one, what if your graph looks like this? What's going on there?
He got his dinner, ate it, and then just.
Yeah, he's still moving, but he's slowing down. And you can tell he's slowing down because you see from, like, okay, here's the line for 1. So it's a little above 1, see? And then this one is like right at 2, whereas this one was a little above. And then this, look, he didn't even make it to 3. So he's covered a little over a meter in 1 second, then a little less than a meter, and then a lot less than a meter as each
And
second
then
goes
he
by.
actually decreases.
He's
That means
decreasing.
he's going
So it
backwards,
says,
right?
no, it's not going backwards. He's
Well,
going forwards at a decreasing speed.
Well, at the end, there dips back down.
Well, that's because I can't draw. It should be like, anyway.
Okay.
So the sentence for that says he slows down so as to actually bite the antelope and not run right past it. But he's got to slow down to catch it, or he'll just keep barreling on past because he's a cheater. Yep. So velocity is what? Somebody describe velocity to me. What's velocity versus speed? Yes, Cole.
Velocity, the speed and direction in which an object is moving.
The speed and direction. Okay, so it's speed
30
plus
miles per
direction.
hour forward.
Yep, 30 miles per hour in this direction or in that direction. Okay, so that would be velocity, and you have to include a direction. And velocity is a vector. So this is velocity is a description of both speed and motion. So velocity is a vector.
It's a cartoon character.
You can add 2 or more velocities together with vector addition. Okay, so that was pretty much your whole lesson, right? So here is what I want to go over with you, because I went over it with the other group, and I want to make sure you know how to do it. So we didn't really go over this too much this year. When we get talking about doing the actual math, let's get to it. When we get talking about doing the actual math, there's a lot of metric conversion, right? Okay, so you're going to want to write this down. Okay, this is what you're going to want to write, because hopefully this will be like a cheat sheet for you. Or if nothing else, it's easy to memorize. Well, gosh, I cannot write up there. Because I'm short. I'm short.
It's not my hand.
Yes, that's a K. It's just mess.
Okay.
And come on, man. You got to get it together today. You're like chatty. All right, so these are your metric units, okay? And this is how you're going to remember them. So this one in the middle. All right, question. What is the unit for volume in the metric system?
Ounces.
No.
Liter.
Liter. Okay.
Why is it an O?
It's not an O. You'll see in a minute. It looks like an O. It's a circle. Sorry. It's a big circle. It's not an O. What? Sorry, that was confusing. I should have made it bigger. But anyway. All right. How do we abbreviate liter? What does it look like?
L-I.
No, just an L.
L.
Okay.
Yeah.
All right. Now, what is for distance, which is also
Meter.
length?
Meter.
Okay. Meter. And how do we abbreviate meter? Small m, right? Okay. What are we missing? We have distance, volume.
But we write these all next to the O?
Huh?
All get next to the O?
Yeah, it's a big circle. Sorry, I didn't make it big enough. Make it bigger. It's just, I'm gonna put the word unit in here. As long as you have it big enough to write the word unit, you do
Is
that.
that an L or a 1?
That's an L, liter.
So
There you
KHDDCM.
How about mass? Do we remember mass?
Wait, are we,
Okay, write that.
I
What do we
not
do?
big enough at all.
It's all right.
I did not.
Well, move around. Flip your paper over. Do something. You got that? You got mass. Okay. You're doing good. See that? Anything else in theirs that would be helpful to you? I'm just looking real quick at their stuff. All right. So what do we use to measure mass? What's our unit?
Grams.
Gram. All right. And how do we abbreviate gram?
G on.
Just a G. Okay? All right, now. Here's where the fun starts. Woo-hoo. All right. These are our prefixes that go in front of these units. So this is going to be
Kilometer. No.
King Henry died.
You died?
I get it. Drinking chocolate milk.
Something's up.
Okay.
Yeah.
Yeah.
Well, I hate milk and I hate chocolate, so of course
You
I'm
hate
dying
all the
for
good
it.
things in life.
So for the unit, mm-hmm,
Okay.
mm-hmm, yep.
Just remove
So,
a random word.
for unit,
And
if you want to just remember that unit is what goes here. The word that you put here is unfortunately. So if King Henry died, unfortunately, drinking chocolate milk. If you can remember that this is unit, and then you know what all the units are. But if you want to remember one of the others so that it'll help you, you get laughing. He died laughing, drinking his chocolate milk. He died Monday. This is the one you hear most often. King Henry died Monday, drinking chocolate milk. Okay, and that's to help you, because most people would just remember, oh, meters, so that's the unit, and they go from there. And then you can say grossly. I'm not even sure it's really a word, but it's pretty gross to die drinking chocolate milk. Potentially nasty. Mhm. So then,
King Henry drinking chocolate milk.
Ew.
Henry died drinking.
so then what happens? All right. So then what happens is these all mean something. So this means kilo. This means hecto. This means deca. Now sometimes you'll see it spelled with a K. It's kind of weird. Dick. This one means deci, centi, and milli. Okay? Get that. And then I'll tell you what they mean.
What's the K under DECA?
Because sometimes you see it with the K. I don't know why. Truthfully, usually you see it with the C, but sometimes with the K. It's kind of odd.
Thank you.
Deck.
All right. So this is abbreviated with just a K. This one is an H. These are all lowercase,
My favorite letter.
always. Shh, you with me?
Yes.
All lowercase, always. This one is usually a DA, but I've occasionally seen it as something else. We'll go with DA, okay? This one's just D, this one's just C, and this one's just M.
Or MM.
No, M,
This is milli, not millimeters.
right, M. So, now, this one's gonna be like the other red one, never erase, let me see. Because I got a new red one, so that last one's so
Never
careful. What do you know? All right,
Who made that noise?
so, kilo means times 1,000, which is the same thing as times 10 to the third. Make that next a little smaller. All right?
Big chart.
And how do we know it's 10 to the third? Because we have, look, 1, 2, 3.
Yeah.
Right? All right. This one is times 100, which is also the same thing as times 10 to the
Second.
2, because you have 2 zeros. Got it? All right. And then this one is times 10, which is the same thing as times 10 to the 1, which is the same thing as times 10, right?
Yeah,
This one's your unit, and you always want to think of it as just 1, okay?
King Henry.
So if this one is 10 to the first, and it's times 10, this one is times 10 to the negative 1, okay? And this one is times 10 to the negative 2, and this one is times 10 to the negative 3. So, how do you use that information? If you want to know how many millimeters are in a decameter, which way would you move your decimal that exists at the end of your whole number?
10 to the power of -2.
So if you want to go from here to here, which direction are you moving your decimal?
Left.
Right. The number is going to, how many of these go into that? And how many of, okay, I'm not even, let me try this way. This is the easiest way. So, you have your King Henry died something, drinking chocolate milk. Okay, you now have, somebody says, I have 252 centimeters, and I need to know how many hectometers that is. Okay? You start here. This is where you are. You're at centimeters, and you want to go to hectometers. So what's the difference? 1, 2, 3, 4. All right? If this is your number, you're going to take 252 and your imaginary decimal, and you're going to move it 1, 2, 3, 4.
So times
It goes
4.
there. Yeah. So your number becomes 252,000. Right? So you put your comma in. Now, conversely, if someone says, I have 384 decameters, and I want to know how many millimeters that is. You start at deca, and you go 1, 2, 3, 4. This one's also 4, but it's 4 the other way. So you've got your number, 384. There's your decimal. Where are we going? 4. 1, 2, 3, 4.
Oh,
So you're your answer.
You did 0.284 when it should have been 0.3.
3. Sorry, 3. You're right. I'm looking sideways. I can barely see what I've got. You're right, 3. So if you're going from top to bottom, you're moving this way because your number is getting smaller. If you're moving from bottom to top, you're going this way because your number gets bigger.
King Henry died outside drinking chocolate milk. It's right outside in the middle.
Yeah. Okay. He's saying it's an O. So does this make sense? How you do this? Okay, the other way to do it is conversion factor. And the other way to do it looks a little different, but it's like this. Say you have 300, we'll do it 384 again. 384 centimeters. We want to know how many meters. Okay. This is the fraction problem. This one's the counting in the decimals. This one is the fraction. So you have to decide, what do I like better? Fractions or decimals? So you take 384 something, and you're going to multiply it times something that's going to give you something with meters. So what you want in this case is, what do we want to get rid of? Centimeters or meters? What are we trying to get to? We're trying to get to meters. So what do we want to get rid of? Centimeters. Okay, but we need to use meters because that's what we're trying to get to. So what you have to do is you have to put centimeters on the bottom and meters on the top. If you do that, you can cross out the centimeters. Okay, so how many meters are in a centimeter?
Quite a
That's the question. How many meters are in a centimeter?
Oh, quite a few.
Not 100. They're not 100 meters in a centimeter.
No, a single centimeter, how many meters in a single centimeter?
Huh?
How many meters?
So what would it be? Or what, how would you do this?
Zero what?
A centimeter is
Zero
what
and-
fraction of a meter?
0.001.
Right, but if we're doing it as a fraction, a centimeter is what fraction of a meter? Here's your meter stick. Look, here's the meter stick. See it? How many centimeters are on it?
100.
100. So 1 centimeter is what fraction?
0.001.
Fraction, not decimal.
100.
1 over 100 is 1/100th. So then you say 1 meter, 100 centimeters. So now you can cross these out. You get rid of centimeter, you get rid of centimeter. So now you have 384 over 100, and then you have meters. That's what you're left with. So then you have to do this division. And when you do this division, you're going to end up with this. So that's how you do the conversion factor. Personally, I think the counting one's easier, but when you get into like chemistry and some of the other sciences, that conversion factor becomes hugely important.
Cool.
Okay, so
So I'm a king.
let's look over some stuff before we wrap up and make sure that everybody's cool on everything. So, how are distance and displacement different? Can somebody tell me?
Displacement is just the line from start to end.
Okay,
Distance is length traveled in total.
very good. All right. So, on your homework, there was a question that said you traveled east 10 blocks and then you backtrack west 4 blocks. What distance did you travel, Cole?
You traveled 14 blocks and the displacement is 6 blocks.
Correct. Does everybody understand why the displacement is 6 blocks?
Because you walked back.
Because you walked
You
back.
went forward 10 and then came back 4. So in total, you walked 14.
14
Your
blocks.
displacement is 6. So it's 10 minus 4.
Does everybody understand why it's 6? Everybody gets it. Okay, good.
Plus -4.
All right, so the next question on your homework said, your family drives 20 miles into Atlanta for a concert. You leave home at 4 p.m. This is a realistic scenario. So though your dad was whipping along Georgia 400 for the first 10 miles southbound at 75 miles per hour, there should have been a comma there, and nobody caught that. That was what cracked me up. Everybody caught the "and" or whatever it was.
Wait, where? Where's that? I just want to.
After 75 miles per hour. He soon reaches a typical, Atlanta, what? Backup, right? Welcome to Atlanta, traffic. Typical Atlanta backup, and before you know it, you're at a standstill for 15 minutes. It turns out it was the result of another cow truck dumping bovine all over the highway. Do y'all remember when that happened last time?
Isn't bovine poop?
No, it's cows.
Oh.
Yeah, do you remember when that happened? Yeah, cows all over the highway.
Oh.
As you finally pass the scene of the accident, you peer out the window to see a deputy chasing a terrified cow up a
I saw the
hill.
video of that. It's
This
so
actually-
funny.
It is hysterical.
I've never seen it.
You
There's like
arrive,
5 officers chasing
yeah,
this cow,
this
and
one
he's
cow,
driving along,
yeah.
shoots them all out.
Yes, I remember it.
so you arrive at the concert at 6:30. What was your average speed? Okay, here's the question. Wait a minute. Here's the question. What information in that question do you not need?
All about the
No, you don't need anything about the cows. So why does that get thrown in there
To
sometimes?
throw you off.
To throw you off, or more to make sure you know how to select what's important rather than to throw you off.
Oh.
So does anybody know what the answer was? Do you
8 miles
remember?
per hour? No.
It was 8 miles per hour because it took you 20 miles. It took you, 2.5 hours to go 20 miles. Because you started at 4:30, you got there started at 4, got there at 6:30. All right, so at the bottom it said, hold on. At the bottom, at your homework, there was a picture of a graph. And it says, imagine a scenario in which you've plotted this graph based on data you collected from an experiment you conducted. What was the experiment and what might the data mean? Does anybody, wait a minute, I'm still talking. Does anybody want to share what they wrote? Even though your homework's not in your hands, does anybody remember what it was? Or care to share it? Lily, what'd you do? Or you still have yours with you? Okay, cool.
I said it could be the average speed in a bike race and the graph of the
Okay.
I understand that question wrong.
It's probably not an average speed, but it could be average speeds every 10 minutes. That could have been the case. It could have been the average speed taken like every 10 minutes because it's a constant speed. Between like 0 and 10 minutes is definitely constant.
Every 10 minutes.
What
10
happens? Seconds, sorry. What happens between 10 and 20? Does anybody know what happens between 10 and 20?
Nothing.
No motion. So if Lily's example is a bike race, between 0 seconds and 10 seconds, they go 15 meters, and then what happened? They just stop. So what might have caused that? 15 meters isn't very far. Yeah, a wreck, or maybe you start to pedal and
cow
your
went on to
cow. Your shoe came out of the clip. You realize you have a flat tire. All right, and then from 20 seconds to 30
It's
seconds,
so big.
you're speeding up again. And then what happened from 30 to 50?
It decreased. I don't like numbers.
Yeah, there was a big decrease, and down he went. So what could have happened there? So like, well, I'm imagining like if it's a bike race, like maybe he starts and then he's like, oh, I have a flat tire. So he looks at his tire and goes, well, there right ahead of me is, wait a minute, right ahead of me is the repair tent. So then he pedals over to towards the repair tent for 10 seconds, and then it takes him 20 seconds to slow down and roll in. What are you gonna say?
If you're wearing shoes with laces, they can get stuck in the pedal.
Yeah,
possible.
you had this
That would
happen.
be
You're speaking from
I hate that.
experience.
Long pants and it gets stuck in the gears.
I don't know, but one time I got it wrapped up so bad, I think I had to cut it actually, because I could not.
Better than getting your having your barefoot issues. Have you ever seen those?
Yeah,
I've seen frightening pictures online. All right, now we're gonna try a real life example of speed. So I got a nice big blob of honey.
What's that?
Hang on, I couldn't hear her.
Do we need to turn off our homework if we just graded it, or do you?
Turn it in so I can mark it. But that's easy. All right, so I'm gonna measure out. The last class I measured out like 5 centimeters and it moved really fast. So I'm actually gonna do it a little bigger. I'm gonna go like 8 centimeters. Okay, so from here to here is 8 centimeters, and I'm gonna tip it, and we're gonna time it. Does anybody want to venture a guess as to how many centimeters per second this stuff is gonna move? Anybody want to guess? 8 centimeters. Do you think it's gonna take 1 second to move these 8 centimeters?
8 centimeters.
1 centimeter was 8 centimeters. So how long do you think it's gonna take it to move 8 centimeters?
4 seconds.
4 seconds.
Yeah, 4 seconds.
So 4 seconds to move 8 centimeters, and or 3 seconds.
Find out next time after this ad break.
Okay,
6.9.
so I'm going to start the timer when I tip the plate, and y'all watch. You ready? And go.
That's a
See
slow
it?
boy.
Oh, okay. Yeah, I'm wrong. I'm
More
wrong.
like 7. We're at 6 seconds already.
Yeah, hold on, I'm gonna stop.
Dang.
9,
Turn it where I can see it.
10. Stop. 12
So
seconds.
12.79 is what I got.
12.8.
Okay, it's close enough. So let's say it's 12.8. Let's just round. All right, 12.8.
12.6.
So it went 12. So we want to know how many centimeters per second, correct?
Yeah.
How many centimeters did we go? We went 8 centimeters and how many seconds?
12.
12.8. Okay. Oh boy. 12.8. And this would be like 8.0. Okay, so
Got it. No, wait.
do you have it?
Wait.
This is centimeters and this is seconds. So what do we have? What's the answer?
0.65. I divided.
0.625 what? Centimeters per second.
That's very slow.
0.625. So a little more than half and a little less than 3/4 of a centimeter per second. That's how fast the honey was. Exciting. Wow, now you know. There's also the how quick can you grab the meter stick experiment, where someone stands and drops and you try and grab it.
You're trying
The cool thing is-
There's a brain games one where the guy goes to a bar and it's a $100 bill and he says, if I drop
Oh,
it,
I've
you
seen
catch
that
it.
one where
And then
it
if
is.
you catch it,
Yeah.
you have to catch it before the guy drops it. So he's like, you have to time it
I
right.
think you have to. Yes.
So
You
look,
have to
I'll do it. Who
grab
wants to be the
before
guinea
you
pig?
drop.
I'll drop. You, come here, Aaron. Come here. So Aaron's the guinea pig. Somebody needs to time. Cole, you time?
Oh yeah, sure.
Okay, so you're gonna stop it the second you see his fingers grab. All right, so I'm gonna hold it above. I should put you down a little lower. Yeah, 'cause I'm not that tall. Okay. You're gonna start it when I say go. Or actually, I can't say go because it'll mess him up.
When
You
you
have,
drop it.
you have to watch.
So
Yeah.
when you let go.
When I let go, you start it. When he grabs it, you stop. Okay. Okay. So 7
That
came
was
in
like
right.
0.75.
Okay, 0.75 seconds, and he caught it at 42. So, oh yeah, I'm fine. I was just, whoa! You're fine. So that's funny. So 42.
Jeez.
So 42, it was, well, he caught it like this. So I'm going to go in the middle. I'm going to estimate. So it took 42 centimeters. So how fast was the stick traveling? It was traveling 42 centimeters in how many seconds?
0.75.
0.75. So it
That's not-
was
it was less than that though, because I thought it took him longer to grab it.
0.75, we'll say, and it went 42. So what's that math, Paul?
Like
What?
What's that math?
Your name is not cool.
42 divided by 0.75.
Last time I checked it, Ace.
It's at 2 now. 42 divided by 0.75. 56.
56 what? 56 centimeters per second. Okay, here's your question. If it was 56 centimeters per second, how many meters per second was it?
Less than 1. Oh. Less than a bit more than a half.
How do you do it? What are we starting with? Centimeters? Where do we need to go?
0.56.
0.56. Correct, because you're counting 1, 2, and you scooch it over. So you get 0.56 meters per second. Right? It's like your ego. It's just what you need. All right, there we go. Just what you need today. All right. Does everybody understand this stuff? Yeah, kind of know. Where are you lost?
My ego.
Oh, no, I got it.
You got it?
Your
Oh,
ego,
indeed.
you lost your ego.
So
I didn't lose my ego. My ego's expanded.
next week,
Unfathomable.
that's
You lost
fabulous.
your ego.
Unfathomable.
You lost your ego.
Let go of your ego.
So next week we're gonna do, let me get there. So next week your class is the same chapter, right? You're staying in the same chapter, but you're reading the next part of it. So it's should be much less reading from here on out, right? That wasn't terrible, was it? It should have been fast compared to what you've been doing. So next week it's also motion, but we're going to be discussing velocity and acceleration. And here's where we get into what acceleration means, and it's not quite what we all usually consider it. And then our lab for next week is, so this one is a velocity and acceleration lab activity. And how does changing the angle of an incline influence the velocity and acceleration of an object rolling down it? So we're going to use things like piece of wood, or and we have a Hot Wheels track, okay? And we've got really cool I got a whole bunch of Hot Wheels tracks. So and we're gonna get some little cars and roll it along, and it should be fun. And you'll be changing the angle of your
I
incline.
had like 10 of those.
You have what?
I had 10. I was talking about.
Oh, the cars?
No, I had a ton of Hot Wheels.
Yeah, the cars were ridiculous.
I
You had more
mentioned
than that.
Bakugan. I had like 10 of those.
Oh, Lord, everybody had Bakugan, man. That was the thing.
Beyblade was still better though.
Yes,
So
it
hang
was the
on.
best.
One more thing real quick. Next week's RICO is National Constitution Day. National Constitution Day. Henry, unnecessary. Y'all, everybody.
Nothing is
All right.
necessary that we're saying.
There's more
Truth.
song?
Okay, let me look at the test real quick and see if we can go over that for just a minute. Let me take it off. Whoops, take off the
What
screen.
respect your hustle making this test run like literally midnight.
Yeah, I do that probably more than you imagine. This
Yeah,
last go round
like,
especially.
It was like 12:03 a.m. on some.
All right, so stop my screen. All right, there we go. Now I'm gonna look at my, you okay over there? You're chitty chatty. Oh, you're singing. Okay. Let's make sure we know what to study. Do we all know what to study? No, we don't. So let's be sure we're ready.
All timing.
Okay, be sure. Henry, sit down. Okay, you're gonna wanna be able to explain why a frame of reference matters when describing motion.
Like actually explain it, or just copy
I'm trying to get
this from notes.
Well, you shouldn't have your notes open when you're taking your test unless that's what your mother prefers you do. So I would say, yeah, so when you're taking your test, it's up to your parents whether or not your notes are open. My preference is that they're not, but that's up to your parents. That's not my call. All right, so you're going to want to be able to match vocabulary with its definition, and you can find all that vocabulary at the beginning of your chapter. You're going to want to understand the ratio of distance of an object to the amount the object moves.
Wait, what's that again?
Ratio of distance. Hang on. Now I gotta go back. I want to make sure I say what I was saying.
Ratio distance.
Hang on. The ratio of the distance an object moves to the amount of time the object takes to move, right?
Wait, what?
Distance to time. The distance of distance and time. The ratio. And you're going to want to understand the different kinds of speed, like instantaneous and average. You're going to want to be able to explain the difference between distance and displacement. And you're going to want you're going to want to be able to describe what the four different graphs that we Cole, the four different graphs that we made. You're going to want to be able to explain what they are. And then you're going to want to be able to read one of those graphs and determine speed. How many meters per how many seconds or whatever, okay, at various points. You're going to want to
there.
They're done, coming down.
Oh, that's a stampede. That's not children.
There's no difference.
No.
You're going to want to discuss distance and displacement from a model or diagram. Analyze it. And that should be it. So if you guys do that, you should be good to go. Don't forget, if you haven't completed your lab, to turn your lab in. If you have completed your lab, then you're good to go. Everybody's good.
What time does Spanish start for us?
12:30. You got 4 minutes.
12:30, you mean? You mean 1:30, you mean? 1.
I mean 1:30. I'm
Or
sorry. You know what I meant.
Late.
1:30. Sorry.
4 minutes.
Hmm?
4 minutes or 12?
4 minutes.
4.
Sorry. All right.
Oi.
Oh,